Welcome everyone to Maya HTT's Engineering Tech Talks. Today we will focus our discussion around a very special topic, cold chain management. Since the 1990s, Maya's advanced simulation solution engineers have helped many companies design better passive and active shipper packages. For many engineers, designing cold chain packaging solutions to comply with industry standards such as the FDA standards, ISTA and TR39 has been quite a challenge over the years. And in the end, when you look at the highly varied external ambient temperature profiles, humidity profile, and transportation situations, and even vibrations, structural elements, it's not easy to ensure compliance, especially on package journeys, which can easily last more than 96 hours, and in some cases even longer. So of course, as the attention has shifted to the promise of many different COVID-19 vaccines, cold chain management is taking its turn into the spotlight. People have woken up to the fact that the hurdles don't stop with the development of just the effective vaccine. The next challenge, as everyone has now heard in the news, is to ensure fast and efficient distribution of this temperature-sensitive product. So with us today, we have Jean-Frédéric Ruel from our thermal simulation group and Alex Marotta from our industrial IoT and machine learning AI group. Jean-Frédéric, let's perhaps start with you today. You have been helping many of our customers to improve their cold chain designs. And perhaps you could help us better understand the different materials and highlight the general simulation best practices or pitfalls that you have been confronted with while helping cold chain engineers.
Yeah, sure. So when we talk about cold chain, typically it's a lot of different materials. You can look at cardboard that usually composes of the outside box of the shipper. You have many different foams as well as phase change materials. So like your typical ice packs that you might put in your lunch or in your cooler to keep your beer cool. And these materials aren't your typical construction materials, so they have better or worse thermal characteristics. Obviously, the foam usually we use because it has a low thermal conductivity, and things like density and thermal conductivity are key thermal characteristics that you need to have a good handle on. So you can look at online databases for sources on those types, or sometimes experiments need to be run to get those types of values. But once you do get the thermal conductivity, density, and heat capacity, those are the main three sort of material properties you need. Specifically talking about the phase change materials. So phase change materials are materials that change phases, so from solid to liquid or solid to gas. So the most typical material used for that is water or solutions of water and other additives added to it. And the main goal of that is that it carries a large amount of heat. It has a very high heat capacity, and when you're changing phases, you have a lot of heat going to the process of phase changing. Now in the simulation, it can sometimes be tricky to capture that accurately. So you do need to have the proper phase change properties for your materials, that being the latent heat of phase change, as well as the temperature at which that phase change can happen. Typically in theory, we often see that it's a single temperature, but in reality, it's more like a range of a few degrees. So for water, for example, pure water, it'd be around 0 Celsius. And depending if there's impurities in the water, it could be a delta of 0 to 1 degree Celsius where that phase change is happening. So once you have your material properties properly defined and sourced, The next sort of unknown in the simulation can be contacts between surfaces. In a shipper box, often you have these different materials, plastics touching cardboard, or the weirdly shaped phase change materials that freeze, unfreeze, which can lead to different contact points between the different bricks and products. And that in turn causes thermal resistances between the various objects. So you need to keep that in mind. Unfortunately, there's not a lot of experimental data on cardboard to plastic contacts or things like that. So it is the typical approach used there to characterize those contacts is a sensitivity study on how that affects your results. But once you are used to the same materials and certain configuration in your boxes, you can reuse a lot of these values from one simulation to the next. Another portion of simulation that you need to remember is anytime there's air is good because it has a very low heat conductivity. But as soon as the gap becomes very big, you start getting natural convection, recirculation, and that can lower your insulation. Now, in order to properly capture that, there's various ways to do that in simulation. You can do CFD, or you can use empirical correlations to take that into account. Now, depending on the size of your model, the size of the gap, different approaches may apply. In all cases, though, it's always preferred to not use CFD if possible because you encounter a very much CFD is a lot more computationally extensive than a purely thermal model. So we always try and avoid using CFD if at all possible to speed up our runs, because a faster run means that you can try more designs and you can you can optimize your designs that much faster, and you can save on running actual experiments later on. And I think that's a topic that we might discuss later. And finally, just to wrap that up, and another important point, and it comes back to why we want to speed up these simulations as much as we do, is these shippers, like Remy said earlier, go through a very long transient ambient conditions. So these can last hundreds of hours. And so, and they can experience very hot temperatures, very cold temperatures. It's also important to not forget that it might receive direct sunlight. So radiation is also an important thing to not forget in these analyses. And thus why not using CFD, having proper element counts, things like that are all key points for optimizing your runtime for your simulation.
Wow, thank you, Jean-Frédéric. I mean, these are great insights, and it kind of reminds me that although a package doesn't look like much when you get it, it's cold chain packaging is a whole new level of engineering, and the details that are to be taken into account are great. So yeah, given the need for designing for those long transient journey, perhaps you could expand, Jean-Frédéric, on how cold chain management would benefit from thermal simulation as a whole in general, or specifically if you have specific kind of benefits you think of when you help our cold chain engineers design their packaging.
Right. Well, I think cold chain and any sort of industry sort of has the same benefits from simulation, and that's for quickly optimizing designs. Running experiments, especially in cold chain, if you're running an experiment in a chamber, it takes 96 hours because your chain, your ambient conditions take that long for the profile. So with simulation, if you're avoiding CFD and running pure thermal simulation, those can run in 20 minutes. So in 96 hours, I don't know the math, but you can run a lot more simulation than you can run experiments. And with that, you can vary thicknesses of your phase change materials, thicknesses of your foam, different contacts between them. So you can quickly evaluate different designs. You can also test different profiles, see which profiles have what kind of impact. One package might be good for one sort of profile, but this for a different kind of profile, it's not appropriate. You can reduce the number of physical testing. I don't think simulation is there to completely replace physical testing, but you can run 20 simulations and just one experiment on that final design, instead of running 20 experiments that each take 96 hours and that each one you need to create a prototype for. And you reduce your cost because simulation is a lot cheaper than experiments. You don't have a lot of the same hardware costs and technician costs. Yeah, and finally, you can, by being able to really optimize your design, you can ensure you're meeting or even exceeding quality standards. And for example, that -70 Fahrenheit temperature level that the COVID vaccine needs to keep, well, you can ensure that that stays the whole 96 hours of your trip of the vaccine.
Indeed, Jean-Frédéric, yeah, and certainly even more so when vaccines have those kind of stringent quality standards for it, especially the COVID one. I mean, others were still pretty high in some cases, but in the early vaccines anyway, there's some that might not have such stringent standards or restrictions or constraints, but certainly for the first few ones that we're seeing now. And by the way, for 96 hours, that would be 288 designs that you could you can try out, or simulations that you can try out during that same time. So it's kind of a nice round figure, almost 300 times more than one test or one validation. Anyway, so yeah, it kind of leads itself now, yeah, in terms of following or meeting or exceeding those industry standards. It's kind of interesting that now more and more instrumentation goes behind this, and the actual temperature of the goods during the entire transportation during that journey could and can be tracked to include certification that the temperature sensitive goods like vaccines did indeed stay within that viable acceptable range. So Alex, maybe I'll turn it to you, and you can maybe highlight some of the real-time industrial IoT platforms and systems you have put in place in some various logistics and transportation use cases and existing clients we have. And maybe that could apply in a nice way to the cold chain management topic of today.
Yeah, thanks, Remy. So what JF has mentioned today, I think, is fantastic during the design phase, and the tools and technologies used that we're using in fleet tracking and logistics at different customers can definitely be applied to cold chain for monitoring things like temperature and really any other parameters in real time during the transit of these packages. So I guess I'll first start with the data collection side. So we're in a pretty exciting time right now where there are lots of options for data collection using cloud and edge technologies. So in the case of cold chain, these packages, they're being shipped all over the country or even internationally. So I think there's a lot of interesting challenges that need to be addressed there, since you can't rely on the typical IT infrastructure or a stable network connection, since it won't be available at all times. So having reliable data collection when that network connection isn't available is a must. There are lots of options today for low energy, small form factor devices, such as Raspberry Pis or Arduinos and other, that you can set up to perform data collection at the edge for these packages using different IoT tools an example is OSIsoft's Edge Data Store. So having the ability to, buffer the collected data when those networks aren't available. So making sure that data is still being collected and held so that it can be transmitted back to your collection system when the connection's restored, which will let you analyze it all down the road. So yeah, then once it's collected and it's been sent off to some central system, you need to pick what that system is where users are going to analyze it. So using IoT-based tools from really any of the major cloud providers, OSIsoft Cloud Services is one that's great for that. But Microsoft Azure, Amazon AWS, Google Cloud, they all have different IoT suites that will help you collect and aggregate important process data, or in this case, temperature or vibration data, and make it available for really any other tool to do analysis on. So with those tools, your end users can build dashboards to view, historical trends of the temperature profiles that JF might be predicting. You can also set up reports to track the compliance, make sure that you stayed within that minus 70 degrees throughout the whole voyage, and even set up notifications if there's a chance that it's going to breach that limit along the way. And then with all that data you're collecting, there's lots of possibilities of machine learning, AI, other analytics that can be done on top of that.
Yeah, thank you, Alex. I mean, that's very insightful to go from simulation to the real-time monitoring and notification, and now the promise of AI and machine learning. That's quite good. And indeed, the data collected, it does present new opportunities for many of our customers that they didn't have a few years ago. So that reliable edge data store you talked about from OSIsoft or other components from different vendors are great enablers. Also, Jean-Frédéric, we spoke about the best practice earlier. Another best practice and another open avenue, AI is one thing, but also reusing the real-time telemetry to enhance the simulation model might be of interest and of value to our engineering groups and engineering clients that we service. So maybe you can talk a little bit about how you could see engineers leveraging that real-time telemetry to enhance perhaps the material characterization of the simulation model, the variance of it all based on real-time, real values that come from the outside world. Can you jump on this a little bit?
Sure. Yeah, so obviously having actual temperature data from the actual run would enable us to look at certain uncertainties in the model. So like I said before, those contact interfaces, the material properties for the foam, how they change because some of these properties aren't necessarily constant. There are some materials that their thermal conductivity varies with temperature. So there are certain unknowns that you can ensure that your simulation properly reflects the actual data, and then you can use these factors learned in your by correlating in your future designs. And you can do sensitivity studies, a little bit by hand, or you can use tools like HEEDS for design optimization, but also design space exploration that automate this sensitivity study quite easily. And if you have data that comes from your actual shipping, you can really mesh these two to build better simulation tools, and at the end of the day, build better shipper products.
That will definitely enhance the cold chain management chain, that's for sure. Yeah. Well, the more I hear about both of you, the more I think we're close to realizing what a lot of people call the digital twin, or whatever engineering group are driving towards these days. I see a little bit of a nice niche and opportunity maybe for even generative adversarial designs there, but we'll talk about that in a different tech talk with Maya. So great stuff, guys. Thank you both, Alex Marotta and Jean-Frédéric Ruel. Thank you for your time today. I hope our audience have learned a few things. And if you want to learn more from MyHTT's cold chain management solutions, don't hesitate to contact us by email at info@myhtt.com. If you can put cold chain in the subject, that would help us answer you better and faster. And you can visit our website, www.myhtt.com. Have a great day wherever you are. Thank you, and see you next
Thanks, Remy.
Tech Talk. Cheers.